Hello and welcome. This is actually the last video I will ever be uploading for my Process Dynamics and Controls class. This is homework 4, part D. I think this is probably video like 15 or 16, so thank you for watching. And so I will read the problem statement as always. There are going to be three parts in this. The first two are going to be done in Colab or on the iPad, and then the second two will be completed in Colab. So first we're going to explain how cascade control may be used to enhance the control of an exothermic reactor by adjusting the flow of makeup cooling water in the recirculating cooling jacket. And then secondly, we're going to blow the block diagram for part D1 and derive transfer functions relating the reactor temperature to changes in set point and disturbance in the inlet cooling water temperature. And then finally, like I said, we'll go into Colab. We'll simulate the unit step disturbance rejection and set point servo control for the following cascade control system. And there's a bunch of specifications there that we are going to get through. But so without further ado, let us begin. So the first thing that we're going to do here is draw a large diagram for part 1 of this problem. And this is going to include this square here with a mixer going down in. So we're going to draw a mixer, right, and actually we want this in smaller. So we have our box, and we will draw this mixer in red. And then around the mixer, as we mentioned, there's going to be a cooling jacket. And so this cooling jacket will have a flow leaving. And this, sorry, I should label this T reactor. And this flow leaving will also have another flow here going into a TCW box. And this temperature set point for cooling water will have a recycled stream going through this controller back around into this and then back into this cooling jacket. So as you can see this diagram, and we will highlight all the important things that we're going to need for the system. And as you can see, this loop will be very important in our simulation process as it'll allow us to get our equation. And this reactor, which is right in here, is going to be just as important. So let's highlight this also. So let's now get down into part 2, which becomes a little more complicated. So in part 2, we're going to kind of draw a flow diagram. And so we have T reactor, and we're going to draw this as the set point going into a controller. And then from this controller, you're going to be going into the reactor and time controller. And from this box, you're going to go into another box, which is the G of the cooling jacket above the controller, temperature controller. From here, you guessed it, another controller. Okay, just deleted it for some reason. And then from this controller, I'm going to kind of draw just so we can fit. So imagine this just keeps going over to the right. We're going to go into the reactor. And then from this reactor, we're going to have 3 separate controllers. The first being GT. The second being GC. And the third being GQ. Now, the outstream here is going to be temperature of the reactor. So now, as you can imagine, we need to add some variables to the top, which are going to be Q, T, and C, as we just labeled, and these will be going down into the reactor. And so now we are going to draw this as one big block diagram, and so this is going to get really, really small because we're going to do some algebra from this. So we are going to have YSP with this arrow here, and from this arrow it's going to be going straight into a controller. which will then go into a small cube, which we will label as GC. From GC, we go into another controller, which will then be going to GC1. From here, we will go into GP1, and then into another controller. And now this is the first recycle. So this is going to go out and back up to this controller. And going into this controller, we have D going into GD, going into the controller, all the way out to GP2, which will have this cube here, and an outlet stream of Y, and this Y will be recycled all the way back to this reactor. So now we are going to actually make an equation for this. So let's start a new page. And this is going to be Y equals GP2 times Z, which we know that Z is going to be equal to D times GD plus GP1 times GC1 times E minus Z. So now when you substitute that into that equation, you get the equation Z equals DGD plus GP1 times GC1E all over 1 plus GP1 times GC1. Now, we also need to know what our E variable is equal to. And our E variable is going to be equal to GC2 times YSP minus Y. Now, you can even plug that into the Z equation, and you get Z equals DGD plus GP1 GC1 times our E variable. So you're going to actually bring out a GC2 times YSP minus Y all over the same thing, 1 plus GP1 GC1. Just going to plug this pencil in, it's going to die soon. And so from this equation, we can actually plug this back into the Y equation, and you get this super long equation. I guess you can't use it while it's okay. So Y is going to be equal to DGP2 over 1 plus GP1 GC1. This will be added to YSP plus Y multiplied by GP1 GP2 GC1 GC2 all over 1 plus GP1 GC1. And that finally arrives at the final equation. You have a lot of algebra. So Y times 1 plus GP1 GC1 GC2 over 1 plus GP1 GC1. This all equals GP2 over the same thing, Y plus GP1 GC1. And this plus GP1 GP2 GC1 GC2 times YSP all over 1 plus GP1 GC1. And now we're going to actually define some variables to make this easier. This term will be our beta, this term will be our alpha, and this term, since it's the same, will be beta again. So finally, the final equation, Y equals alpha over 1 plus beta times D plus beta over 1 plus beta YSP. We will box this off, and this is the final equation that we have been looking for. But before that, we actually did want to label this. This is the transfer function of the disturbance, and this is the transfer function of the reactor temp. So now we are able to go into Colab. Okay, so as you can see, I have inputted the variables already in the library. And so while we run our library in, I'm going to read you guys the variables. Obviously, KC1 and KC2 are 1, along with our tau initial 2. And then our GP1 is going to be 1.5 divided by 2 times s plus 1. And our GC1 is actually going to be equal to our KC1. And then we have our GD1, GP2, GC2 values all respectively with their equations. Again, this was all given to us in the problem statement. And so now we can actually begin the coding process. So we go below this and we first need our beta and our alpha values. And so our beta is actually going to be equal to GC2 times GC1 times GP1 times GP2. This all is going to be divided by 1 plus GC1 times GP1. And if you remember, this is exactly what we set in our iPad when we were deriving equations. That was when we boxed it off and said this is going to be equal to beta and this is going to be equal to alpha. That way we could rewrite it in simpler terms. So then we have GD1 times GP2. This is all going to be divided by 1 plus GC1 times GP1. And now we first want our inner loop disturbance. So to do this, we're going to have to plot our variables. And so we want t and y underscore disturb. And this is going to be equal to simulation of alpha divided by 1 plus beta. And then here we need lambda t, and we need 1. You want the iterations to be 500. And dt set equal to 1. Perfect. Now we need to do fig. Now let's actually go back to this previous one, and we will copy one of these. Again, this is just because I know that those don't have any syntax errors, and then we can kind of, so this is just like a skeleton, and we're going to fill the meat in. That is the same. We want x to equal t. We want y to equal to y disturb mode lines, and then layout 600, 400, and then we want to show. Excuse me. Alpha dot 1. Oh, sorry, this is supposed to be divided by. Perfect. So for the inner loop disturbance, we see these oscillations starting at 0, and it quickly spikes all the way up to about 0.8, and it goes down to negative just past 5. And then with time, as time goes on and larger, you see it oscillate and kind of find its set constant horizontal pattern at 0. Finally, around about 185, that's when we finally get a constant horizontal line. So now let's continue, and we're going to do this for the outer set point change. And so we will type that out, outer set point change. And for this, we actually are going to copy a lot of this also. It just makes it a lot easier. Like we said, we know that those don't have any syntax errors. So we want y, but this is going to be equal to set point. Our simulation is no longer alpha. It's beta divided by 1 plus beta. Those are going to be the same. We want to make our subplots, except this time it's going to be y set point. Mode lines with the same thing. So we're going to run all, and we get a slightly different equation. As you can see, this one goes positive, negative, positive, negative, positive, negative, all the way until just a flat 0. Until this one, it goes positive, and it does go slope back down again, but it never gets below 0. So we have these positive oscillating values in the y-axis until about, I want to say the same number, about 180. So at least you know at the same time it's going to be flattening out to 0. But as you can see, the oscillations are smaller. I'm sorry, the oscillations are about the same size, but they're just happening at a higher, it is shifted up about 1. Actually, exactly 1, I would say it is shifted up. So that is the point we are currently at. So thank you for watching. This is the conclusion of this final homework for separation or for process dynamics and controls. Thank you for watching and have a nice day.